In the next unit, we'll stay with approximation algorithms, but we'll bring back this powerful tool we've looked at briefly before, namely linear programs, which turn out to be a very, very convenient ingredient to build approximation algorithms. I'll do a quick recap in case you forgot, and also to set the notation, which certainly people will forget over many weeks. And then we'll look at different ways you can use LPs for approximations. In particular, we'll also look at this duality theory of LPs that I left out last time. And this really comes to shine in this chapter. So just briefly to recap, we've talked about this at length in, oh dear, what was it, Unit 6? Something like that. A linear program, and here I've already given the standard form, we'll come back to why that is convenient, is an optimization problem of this sort. You're trying to minimize some cost. You have variables, which can be any real number, but non-negative. You have n of these variables, and you have a linear cost function that gives each of the variables some coefficient. And you have a linear set of inequality constraints, where you can concisely write these m constraints in the matrix notation. If you forgot what these look like, here's what they mean unfolded. But we've dug through that back in the day. Yeah, terminology that we had also last time. So a feasible solution is just some values for x in this case that satisfies these two constraints, these inequalities. We call that ctx, this value, the objective function value. And then an optimal solution is one with minimal objective function value or minimal objective value. And we'll usually denote that with a little star. Here it's formulated to have integer coefficients in all the functions and constraints. You can generalize it to rational coefficients without much happening most of the time. We don't want to have arbitrary real numbers because we need to represent them exactly. Rational numbers is usually fine. You can multiply the constraints and the cost by the common denominator if needed. It will sometimes make a difference though. So it's important to keep in mind that you should say if the coefficients are restricted to integers or not. That was LPs. Here's an example. Some like an arbitrary example that doesn't have a specific meaning. Just to make it concrete, and you can work out that it has a certain optimal value at this point and optimal objective value 26. We also talked at length back then about the geometric view, polyhedra, and extreme points. You can show that an optimal solution is always an extreme point where some of these constraints are met with equality. Instead of the standard form that I've shown you, you can allow equality constraints. You can allow variables that are not just non-negative. You can do max instead of min. All these standard tricks to reformulate LPs we covered back then as well. But you can assume standard form for algorithms because you can transform. In general, such a program can be infeasible, meaning there's no value for x that satisfies all constraints simultaneously. Or it could be unbounded in the sense that you can improve this to infinity or minus infinity for minimization. But the interesting case that pops out from typical optimization problems is that it is finite, meaning there is some concrete finite optimal objective value. Okay, that's what I mentioned. If there's some optimal solution, if it's finite, then there is an extremal point that's optimum, and we can compute those in polynomial time. In practice, the simplex method, but in theory, the ellipsoid method is the one that's guaranteed to be polytime, worst case. You know all this from back then. Just to remind people. The last bit, also repetition. Integer linear programs are almost the same as what I've just shown, except that we have a constraint that things are natural numbers, integral, as opposed to just non-negative. And that somehow seems like a harmless change, but it makes the problem NP complete. Even so, the decision problem would be, is there a way to make the objective value better than the threshold? And so it makes a big difference in terms of how easy it is to solve the problems. But also you can put these in standard form using essentially the same tricks.